Yeah, sorry, it doesn't look like that. It looks like this, right? Where this is 1. What this looks like is where this is 1. Looks like that. And you can only do a Fourier transform if it's absolutely integrable. I don't think this is actually absolutely integrable, but I would have to check. I think this would diverge if you integrate from -infinity to 0. Because the area under this curve is equal to -infinity 0 e to the negative t dt. I'm not sure if this diverges or not. Yes. Sorry? It means that if you take the integral from -infinity to over the entire support of the equation, so -infinity to +infinity, it has to be a real number. It can't be infinity. So it's asking, does it diverge? All right. So going back to this equation, because we divergent, there's not much time left. Right. So we've established what x of f is and what h of f is. So our y of f is equal to 1 over 1 plus j omega times 1 over 1 minus j omega. So from here, you can do something called a partial fraction decomposition, where this is a product of two like imaginary numbers. Yes.
Wait, so if you multiply it out, you get like 1 over 1 plus 4 pi squared f squared, and then there's like a property.
Yeah, you can use that.
Okay.
You can.
Okay.
Just like write it out. There is. But sometimes it might be more complicated. What if there's a third one, right?
Yeah, just don't do that.
Well, I don't know. Maybe it already happened. I don't know. I didn't personally write a question like that, but it might show up. So how you do this? Well, something called partial fraction decomposition is that you basically can write this product of two rational numbers with factors on the denominator as a sum of their individual factors with some constants on top. So it looks something like this. So all you really need to do is solve for alpha and beta. And this is a partial fraction decomposition. If there was another factor, like let's say 1 over 2 plus j omega, then you just add another term where it would be 2 plus j omega. Right? But that's not the question, so we're not going to do this part. So now you just need to solve for alpha and beta. So to do that, we have on the left hand side you want to turn this into systems of equations and then just do algebra to solve for a and b. So to do that, you multiply both sides by 1 over j by 1 plus j omega and 1 minus j omega. So if you multiply this side by those two, you get 1, right? Here, alpha over 1 plus j omega times 1 plus j omega just becomes a, and you multiply by 1 minus j omega. So it'll just be 1 minus j omega a plus, similarly, 1 plus j omega b. You can solve for omega. It's just easier to write this way. You can do whatever way you're comfortable with. So from here, you will get a, 1 second. So from here, if you solve for alpha and beta by using this equation and the shoot. Okay, there's not much time left. What I'm going to do is I will post a very detailed explanation of how to do partial fractions. But if you solve this system, you'll get a equals 1/2, and b is also equal to 1/2. Which is not here. OK. Sorry, negative 1/2. Negative 1/2. Shouldn't it? Pretty sure. Oh, wait. No. Yeah, that's 1/2. OK. Yeah. OK, so now we have our y of f equals 1/2 over 1 plus j omega plus 1/2 over 1 minus j omega, right? Now we can just use our table. So this is like our a. So this is going to be 1/2 e to the negative t us of t plus 1/2 e to the, this is a negative 1, t us of negative t. Yeah. Because this is the reflection of the signal, right? Yeah. So this is your y of t. All right. Okay. If you're still confused about partial fractions, just talk to me afterwards. Actually, no, I have somewhere to go. I'll post a detailed example by tonight on how to do it, because we will update them. We have something at 4. No, we have something at 4, remember? Oh, did you already update? OK, yeah. They'll probably update it by 4 o'clock. And I'll upload the partial fraction example by 6 tonight. Yeah. 7. OK, so the next, I have 2 more problems to cover quickly. One is solving differential equations with continuous time Fourier transforms. I believe this is like the last problem on homework 5. Or sorry, something similar to that, not exactly. So to do this, there's a general strategy. So the question will ask you for like, oh, find the, first up is you always want to find the frequency response, and then do the inverse transform to find the impulse response. And from that, you can also then get the output given some input. I'm only going to have time to show you the frequency response, because that's the most important and the most tricky part. So we're going to find h of f. So we use the fact that h of f is a ratio of y of f over x of f. And this differential equation, we can just, and also we will use Fourier transform properties. So I'm going to rewrite the differential equation. It's y double prime of t plus 4y prime of t plus 3y of t. And it's equal to y prime of t plus x prime of t plus 2x of t. So now the next step we do is we can take the Fourier transform on both sides. So the Fourier transform on y double prime of t using it's the second derivative of just y of t. So Fourier transform y of t is just y of f. And because it's the second derivative, it's going to be j2 pi f squared. And that comes from here, right? Nth derivative, you get j2 pi f to the power of n times the original Fourier transform. So this is squared. Similarly, this is the first derivative, so it's just 4 times j2 pi f y of f plus 3y of f equals j2 pi f x of f plus 2x of f. Right. And you notice that all the x of f's are on one side, all the y's of f's on the left side, all the x of f's on the right side. So you can just combine like terms and then do a ratio to get your h of f. So on the left side, the factors of y of f are negative 4 pi squared f squared, right? Taking the square of that, plus bringing the 4 into the j2 pi f is j8 pi f plus 3. On the right-hand side, bringing factors of x. So it's just 2 plus j2 pi f equals x of f. And now we just rearrange to get y of f over x of f. So our h of f is equal to y of f over x of f. So that's equal to 2 plus j2 pi f over negative 4 pi squared f squared plus j8 pi f plus 3. And I'm going to rearrange the terms of the numerator so it looks nicer, where you have real parts in front and the imaginary parts afterwards. All right. And this is your h of f.
If you ask for h of t, would you recommend not multiplying it out and keeping it a fraction?
Keeping it what?
Keeping it like as a
Factored out.
yeah.
Yes. Yeah. Yeah. That would be easier to do. Great. So then you can do the partial, or you can do, if you get to here, you can then do the partial fraction expansion on this. But I don't have time for it. Yeah. OK. So guys, I have one more thing to cover before we go, because it's been a long 2 hours. So the last thing is that something that Chin-Fu sprang on all of you guys Wednesday's lecture, which is the relationship between the Fourier series and the Fourier transform. I'm not going to go through the proof of it, but I'm going to tell you 2 things. One, there's going to be a problem that is going to use this, and 2, just memorize the equation.
Go back to the slide that had my example of square function. There. All right,
Yeah.
See that? That's very similar to what you have on your Fourier transformation table, that final answer there. If you were to use the equation that Victor just gave you on what's on your Fourier transformation table, you should get that. Okay?
Yeah. So what happens?
An example of where that happens.
Right. OK, so I'm going to explain that part. So if you have like a square function, and just by itself, going from -1 to 1, the Fourier transform is just equal to sine. This is t equals 2, right? Wait, what?
Well, you're at the period is 3.
Should it be just 2? 2 pi k?
Well, the period's 3 here. So
Oh, period is 3?
in this case,
Okay.
I guess it would end up being sine phi f over pi f, I think. Is that right?
Or pi f? Okay.
I'd have to check my table.
Right. Essentially what we're saying is that that equation on the right side, so for x of k, is just equal to 1 over t times the Fourier transform, where the frequency is equal to k over t, which is that equation. Yes?
But we don't know what x is to like.
Right. So this kind of problem, what we'll tell you is that we'll give you some x of t, which is non-periodic. Let's say a triangle, right? From 0 to 1. And then we'll tell you, oh, here's the periodic version of that function, where you just repeat this over its period over and over again. So this triangle looks like this. Right? We'll give you this. So you can do the Fourier transform on this aperiodic function. And you can also do the Fourier series on this periodic function. But instead of calculating out the Fourier series on this directly, you can actually find the coefficients of the Fourier series by using this, this formula. So what you would do is you would find the Fourier transform of x of t, of the periodic, which will be running out of board space. Okay. All right, so we have x of t, which is this triangle. And you have the corresponding like periodic version where you just repeat the triangle over a period. Right? If we ask you for the Fourier series of this, I'm pretty confident you guys can find the coefficients. But an easier way, especially when you have when this shows up on the table, then you can just find the Fourier series directly. And from the Fourier series, if you let f equals k over t, then you can use that equation to find the coefficients for your Fourier series, which is just x of k equals 1 over t x of k over t. To make this less confusing, it's ak equals 1 over t x Fourier series k over t. Does that make sense? Yes.
Is that x the Fourier transform x, or is the x t?
So the x with the square brackets is the coefficients of your Fourier transform. The x with round braces is your Fourier transform, because it's continuous time. That's why I write ak here, because that's less confusing notation-wise. Yes.
Will you ever use this to go backwards?
I don't think you can,
Yeah, no.
unless you do it over all k, which means you would have to, yeah. I don't think it's, you can get an approximation. Because what you're really trying to do is that your Fourier series is a continuous function, but your Fourier transform is continuous, but your Fourier series is discrete. So what you're doing is you're picking like specific intervals, but you lose information in between the discrete values. So you can't go from like, it's hard to do it, but we don't expect you to go the other way. Yes?
It would kind of be like So it's like, let's say you find the Fourier transformation of a signal, and then they're like, okay, here's something that's similar, only now it's periodic.
Like say that signal that you found is periodic.
Yeah, so now what's the Fourier series of it? So instead of recalculating it from scratch, you could use this technique to go that way. Yeah.
I think it's either problem 5 or 6 in homework 5 that you need to use that equation. Yeah. So you can refer to that. All right. I'm already over time, and the last slide I have is just general test taking strategies. I have 2. One of them is do the easy problems first. So do the ones that you think you can complete in like less than 5 minutes. If your attempting problem takes too long, I would skip it and do another problem, and then come back to it later. Second thing, you don't like actually have to make the mind map, but this is how I approach like just any like math or engineering class, because everything is like problem solving based. And what classes do is that our concepts are like our tools in a toolbox. So you just need to know which tools to use. So for example, if we're asking find the frequency response of a differential equation, well, the first question we ask ourselves, well, are we given the impulse response? If we don't, then you can just use the eigenfunction to find the frequency response. If you do have h of t, then you can use the analysis equation or the Fourier transform directly. Yeah. All right, that's all. Review session.
Does anybody have any questions before we?
Oh, I was gonna ask about proofs or like derivations. We don't have, there won't be like anything
There might be.
We don't really. I know Dr. Miller doesn't like derivations.
Yeah.
If any of the TH programs, there's a very good chance that Dr. Miller will. Yeah.